Hello everyone, this is Correlation Sketches for Approximate Joint Correlation Queries. My name is Aécio Santos and this is joint work with Aline Bessa, Fernando Chirigatti, Christopher Musco, and Juliana Freire. The increasing availability of structured data, ranging from web tables and open data portals to enterprise data, opens up opportunities to improve data analytics and machine learning models by augmenting relational datasets. Consider the following example. Suppose a data scientist is building a regression model for predicting taxi demand in New York. She has an initial dataset which includes some features and the target variable that she wants to predict, number of trips. Her model is not performing well, so in order to improve it, she decided to search for additional features that may affect taxi demand. She searched on multiple open data repositories, and she eventually found a dataset that contains weather indicators such as precipitation and temperature. She joined the dataset with her original data and retrained the same regression model. By adding these new features, she achieved a 41% improvement over the previous result. While not described in detail, in our example, dataset discovery is a very difficult and time-consuming task. Datasets are usually spread over many data repositories and systems. Once you find a potential dataset, determining its relevance involves many steps, including making sense of the data, determining if the data can be joined with the original data, and checking for column correlations. While not described in detail in our example, dataset discovery is a very difficult and time-consuming task. Datasets are usually spread over many data repositories and systems. Once you find a potential dataset, determining its relevance involves many steps, including making sense of the data, determining if the data can be joined with the original data, and checking for column correlations. As a point of reference, internal research at Lyft has found that their data scientists spend 25% of their time on data discovery tasks. As I will show next, our work tries to address this problem and make the data discovery process more efficient. Now, suppose there is this search engine that allows you to not only do simple keyword queries, but also search using a dataset as a query. First, it lets you upload the dataset, and then it automatically detects its columns and uses them to find related datasets. As such results, the search engine would rank datasets considering join quality and data correlations. For instance, let's look at the second search result. This search result shows that the dataset can be joined on 4 different columns. It also shows you how good are the joins and the correlation level between the columns in this search result with the columns in the query dataset. As we will see later, there are several challenges involved in the implementation of such a search engine. Let's now define this query more formally. So what we want is, given a query table that contains a join column and a target column, we want to find tables in the dataset collection that are both joinable with the input table and that contain a new column that is correlated with our target variable. To better understand this, consider this example. The key operation in this query is what we call a join correlation. We want to first compute the join between the two input tables on the left and aggregate the resulting values using an aggregate function such as sum, max, or average. Only then we can compute the correlation between the columns x and y. The key challenge in evaluating join correlation queries is how to do so efficiently. Joins, aggregations, and correlations are all expensive, so when searching over large dataset collections, an approach that computes these operations at query time is infeasible. In addition, we can pre-compute them, as we only have access to the data after the query is issued. An alternative approach may be to reduce the input size at the cost of approximate results. To see why naive sampling doesn't work, let's look at our example again. We want to compute the correlation between the join columns on the right, but we only have access to the original tables on the left. It's easy to see that taking independent random samples of the numeric column vectors x and y does not yield valid correlations. The first reason is that we don't know which values need to be included in the join. And the second is that in order to compute the covariance term in Pearson's correlation formula, these values need to be aligned. Another approach could be to take random samples of the complete rows and then join these samples. However, taking independent random samples leads to a quadratic decrease in the probability of a key being included in both table samples. To address this problem, we propose correlation sketches, an extension of KMV sketches that supports joint correlation estimation. The key idea is to use hash functions to create a compact and randomized sketches that summarizes the data in each table, and then, given a pair of sketches, we can recreate a uniform random sample of the joint table without having to compute the full join. Correlation sketches allows us to efficiently retrieve joinable tables using inverted indexes and to perform fast correlation estimation at query time. In order to construct a sketch, we first use a hash function h that maps all join keys to a discrete value. Then, we map the hashed values to a number in the unit range and select to include in the sketch only the rows with the n minimum values. In the final sketch, we only need to store the hashed keys and their respective numeric values. The main reason why this works is that using a common hash function for building all the sketches introduces dependence. In other words, if a key is present in two tables x and y, this means that if a key is included in the sketch for x, then it will also likely be included in the sketch for y. In addition, the final sketch is still a uniform random sample of the table. In order to estimate correlations from a pair of sketches, we can simply join the sketches on their hashed keys, and then we can apply any correlation estimator such as Pearson's or Spearman's. Another advantage of correlation sketches is that it includes all information from a classic KMV sketch. This means that, in addition to correlations, it can also be used to estimate other statistics such as the size of the full join, Jacquard containment, and Jacquard similarity between the keys. To evaluate the accuracy of our sketches, we performed experiments using both synthetic and real data. This scatterplot shows the actual Pearson's correlation on the x-axis versus the correlation sketches estimates in the y-axis. Here, we can see that for data that follows a bivariate normal distribution, the errors are small and the estimates are concentrated around their true values in the diagonal. When we look at real-world datasets, which typically come from unknown data distributions, the estimates have a much higher variance. As I mentioned earlier, if we use estimates with such errors for ranking datasets, we will inevitably place uncorrelated columns on the top of the ranking. We further investigated this problem and we show that it is possible to detect when these estimates are not good, and therefore we can reduce the problems created by noisy estimates. In order to reduce the impact of estimation errors, we designed a simple scoring framework that avoids placing uncorrelated columns in the top of the ranking. More specifically, instead of only using the correlation estimate, we apply a penalization factor according to the risk that the estimate is a bad approximation. In order to measure this risk, we can use multiple statistical methods. For example, we can use the Fisher-Z transformation to compute the standard error. However, this method assumes that the data follows a normal distribution. An alternative approach could be to use bootstrapping methods for computing confidence intervals. Bootstrapping methods tend to be more robust for data from any distribution. However, they are also extremely expensive to compute. To address these problems, we performed a theoretical analysis and we proposed new confidence interval bounds for correlations. Our bounds are both fast to compute and make no data distribution assumptions. More formally, we calculate upper and lower bounds for a given confidence level alpha. Our approach to construct this interval consists in decomposing the correlation into 5 different terms that are sums of random variables. Then, we use Hofding's concentration equality to create bounds for each of these 5 independent terms. Finally, we combine these 5 bounds into a single confidence interval using a union bound. In our experiments, we evaluated 4 different scoring functions based on correlation sketches estimates. The first one uses only the raw correlation sketch estimate with no penalization factor. The other three functions compute penalization factors based on our Hoeffding bounds, on the bootstrapping-based confidence intervals, and based on Fisher-Z transformation standard error. In addition, we consider three baselines. For the first one, we simply draw a random score from the uniform distribution. And for the two others, we consider the Jacquard containment between the keys of each pair of tables. The Jacquard containment basically tells us how good are the joints between the two tables. We consider two variants of the containment. The first one is the exact formula, and the other ones are estimates produced by correlation sketches. Let's first look at the results using the mean average precision metric. The first thing we can notice is that functions based on correlation sketches achieve a better performance than all the baselines. When we consider as relevant only columns with a very high correlation, the scoring based on our Hoeffding bounds attains the best performance. Notice that our bounds can be computed within a fraction of the cost of the second best scoring, which is the bootstrapping method. When we consider smaller correlations as relevant, the functions based on our bounds are still able to achieve the second best performance. We also consider the normalized discounted cumulative gain metric, also known as NDCG. Differently from mean average precision, which only supports binary relevance, NDCG is able to take into account the actual correlation as relevance. We calculated the NDCG scores considering the top 5 and top 10 results. In this case, the results shows that the bootstrapping-based method is the best performer. However, we can see that the performance of our Hoeffding-based method is very close, with the advantage that it can be computed more efficiently. In the previous results, we were looking at the aggregated scores for all queries. Let's now look at the distribution of scores for each individual query. In this figure, the 4 bar charts in the first row shows the distribution of scores for the containment scoring function. The second row shows the distribution of scores for the Hoeffding-based method. In each plot, the bars represent the number of queries with a score within that range. Bars in the left are queries with low scores with values close to 0, while bars in the right means good scores with values close to 1. When we compare the two rows, we can see that there is a significant shift in the number of queries that have a lower score toward higher scores. For example, when we compare the NDCG at 10 scores, we can see that many queries that had low scores with the containment scoring function increase the scores when we use correlation sketches based scoring. Now let's look at runtime efficiency. Our results shows that computing joints and estimates with correlation sketches takes only a fraction of a millisecond. In average, the computation can be orders of magnitude faster than using the full data. When we look at tail latencies, the improvements can be even higher. This level of speedup allows us to perform correlation estimation at query time. Finally, we perform an end-to-end experiment to evaluate querying efficiency. For this experiment, we split our largest dataset into query and corpus set. Next, we created an inverted indexes for the corpus set, and then we run all queries against the indexes. The results shows that most queries complete in only a few hundred milliseconds. For example, for 98% of the queries, the running time is less than 200 milliseconds. These results shows that our approach can provide interactive response times for dataset search over large collections. There are several works that are related to our research. The closest are papers that propose efficient methods for finding tables that have high overlap between the join keys. These methods typically rank tables using Jacquard containment scores, which we also use as a baseline. While approaches such as LSH ensemble, Lasso, and GBKMV are hashing-based methods that solve the approximate version of the joinable table search problem, Josie is an efficient query processing algorithm that solves the exact version. Correlation sketches complement these methods. After finding joinable tables, our sketches can be used to re-rank tables based on correlations. Also related to our problem are works that study estimators and confidence intervals for correlations. There is a vast literature in the field of statistics that cover these problems. Most recent works have focused on studying the effects of non-normal distributions on correlations. We also note that most existing approaches for computing confidence intervals either make data distribution assumptions or are expensive to compute. To the best of our knowledge, no prior work has studied the problem of estimating correlation between unjoined tables. Moreover, some papers study cardinality estimation sketches that can be used for estimating joint size. From these, the closest to ours is the family of minimum value sketches, such as the KMV, which we extend to support joint correlation. Finally, there are several end-to-end systems that deal with different data discovery tasks, such as Data Civilizer, Auron, ARDA, and Juno, which could benefit from using correlation sketches. In summary, in this work, we formalize the definition of joint correlation queries and the problem of joint correlation estimation. We propose an efficient solution for this problem based on sketches, and we also give a new confidence interval bound that can be used for ranking correlated columns. Finally, our experimental evaluation shows that our approach is both effective and efficient. This work also opens up a new research avenue for the development of sketches that estimate statistics after joins. Possible extensions include sketches for spatial-temporal data in different resolutions and other pairwise data relationships. In addition, it would be interesting to see applications of correlation sketches to end-to-end data discovery systems. For example, we would like to apply our sketches to derive table ranking strategies and evaluate the impact of such strategies on the accuracy of the final machine learning models.